Today we'll start with Stokes equation. So till now we have covered conservation of energy, conservation of mass equation, which is continuity equation, and after that we have completed conservation of momentum, and under that we have derived Euler's equation. Then we derived Bernoulli's equation, and then we have derived the formulas for like flow through orifice, flow through Venturi meter, orifice meter, then pitot tube we have seen. And then we have seen one case like how much time it will take to empty a tank. So those topics we have completed in last lecture. Now, as we have completed conservation of mass, then conservation of momentum. Now, this Navier-Stokes equation here, we'll try to see here what will happen when we consider viscous forces. Like we have seen our conservation of momentum equation, where we have seen different type of forces acting on a fluid element. Like if this is our fluid element, so different types of forces which are acting on that fluid element, that we have seen. Okay, so just I will show you quickly. So you see, the basic equation was Newton's equation of motion of fluid, which includes gravity force, pressure force, viscous force due to this compressibility, then turbulence, then surface tension. Okay. Now here, then after this, when we have neglected force due to compressibility and surface tension, then we got Reynolds. Then we got Reynolds equation. After that, when we have neglected that turbulence wala part, then we got Navier-Stokes equation. So this equation only we are going to see now. And here also, if we further neglect the viscous forces, then only, like if we consider inviscid fluid, then only we get Euler's equation. And then we have derived the differential equation, and when we integrate this equation, we'll get Bernoulli's equation. Okay, so in Bernoulli's equation we have not considered viscous effect of fluid. Now here we'll consider this viscous effect also. So in Euler's equation we have considered gravity force and pressure force. So mass into acceleration is equals to gravity force plus pressure force due to pressure. But in Navier-Stokes equation, we'll consider gravity force, pressure force, and viscous force also. Okay. So we'll see viscous flow now. So whatever we are going to study, that is known as viscous flow now. Okay. So for that, the equation will be Navier-Stokes equation. So Navier-Stokes equation is what? Equation. So they can ask this question. Okay, like from this topic itself, two questions can come. Okay, two questions can come. One is which all forces are considered in Navier-Stokes equation. Okay, which all forces are considered in Navier-Stokes equation? So which all forces? Forces are gravity force, pressure force, and viscous force. These three are considered in Navier-Stokes equation. Okay, this they can ask. First thing. Second, they can ask is which equation is it? Like, is it conservation of momentum, conservation of mass, conservation of energy? Options. Okay, so this is conservation of momentum. This is a momentum equation. Okay, now momentum equation, so it should be in a form of what? Mass into acceleration equals to that net force. Now that net force is what? Gravity force plus force due to pressure, then viscous force. Okay, so you see, the basic form of Navier-Stokes equation, the general form of Navier-Stokes equation, you see this actually this particular equation is in per unit volume. Okay, the complete equation is divided by volume, unit volume. Okay, so if we multiply with volume, see if I multiply with volume every term here, multiply with volume. Okay, so you see this is density multiplied by volume. Now density multiplied by volume will be what? Mass. Okay. So this represents what? This wala part represents your mass per unit volume. Okay, which is density. Now this is what? Dou v by dou t. Sorry, total derivative of velocity with respect to time. And in fluid kinematics, we have seen total derivative of velocity with respect to time is what? Acceleration. Okay, so this is what? Acceleration. So mass into acceleration. Now this is equals to, this represents what? Force due to pressure. So this term is there. This represents this two terms. This two terms contains, you see, mu. Mu is what? Viscosity. Mu is viscosity. So you see this two terms represents what? Viscous forces. Viscous forces. And the last term, this term, which is what? Rho multiplied by g per unit volume. So let's say if I multiply by volume and then g, then this is what? Mass, and g, mg is what? Weight. So this is force due to gravity. So all three terms we have seen now. Is it clear? Which all terms it contains? Navier-Stokes equation. So they can ask which all term it contains, which all forces it contains. Okay, Navier-Stokes equation. Now, if we want to solve any fluid flow problem, if we are not considering the effect of energy, only the flow parameters like velocity and pressure, all these things if we want to calculate, then we'll have to solve two equations always. One is conservation of mass and another is conservation of momentum. Okay, this point also you can note. Okay, if you want to solve any fluid flow problem, two things is required: conservation of mass and conservation of momentum. This two equation will have to solve simultaneously. Okay. Okay. Now next is, if you remember, this is our what? Which equation? Which equation is it? Which equation is this? Which equation is this? Continuity equation. Okay. This is also continuity equation, but for any fluid flow, like even if it is compressible flow, it is applicable because density term is inside the differential. For incompressible flow. So you see, this is our continuity equation. Okay, continuity equation. Now, if now this particular thing can be written in vector form like this. This is in vector form. Okay. Now, for incompressible flow, this term like dou rho by for incompressible density is constant. So if the density is constant, dou rho by dou t will be 0, and density will come out from the differential. So you see this equation will get. Okay, and in vector form, this this is how we can write a continuity equation. This is how we can write a vector form. Okay, this one. Now you see this particular thing is there in Navier-Stokes equation. Okay, so for incompressible flow, we know this is 0. For incompressible flow, we know this particular thing is 0. So we can put this term as 0 for incompressible flow. So this equation of Navier-Stokes equation is applicable for compressible flow also. Okay, it is applicable for compressible flow also. But the moment we put this term as 0, because this grade of V is equals to 0 we are putting. So this is 0. Then we are left out with three terms only. This one, and this term. So we are left out with pressure wala. Now again viscosity, force viscosity, and so this equation of Navier-Stokes, this Navier-Stokes equation is applicable for what? Incompressible flow. Okay, so this also they can ask. Navier-Stokes equation is applicable for compressible flow only, incompressible flow also. In general, if they ask, it is applicable for compressible flow also. But if they specifically give this particular term, okay, then it is applicable for incompressible flow. Is it clear? Okay. Now we'll start viscous incompressible flow. So as we are going to start viscous incompressible flow, this equation only we are going to use. Okay. So now we are going to see what is the effect of viscosity when fluid is flowing. Till now, whatever we have studied, there we have not considered the effect of viscosity. We have not considered the effect of viscosity. Okay. Like when we were applying Bernoulli's equation, effect of viscosity was not considered. Only pressure force and gravity force was considered. Now here if you see uh, viscous incompressible flow. So force due to viscosity will consider. Now you see this will be our general equation. Okay, and this only we can write in x direction. Now this equation can be written in x, y and z direction. Okay, and if I am writing it for for any fluid element of volume dv, you see this is volume. Okay, multiplied, the volume is multiplied. So you see this represents mass, this represents your mass. Okay, now ax, this is subscript ax, like this. So ax is what acceleration in x direction. Okay, so mass into acceleration. Now this you see rho into the volume into gx. So this is force due to gravity. Now dp by dx, so here the force due to this one pressure, it is dp by dou p by dou x multiplied by volume, and then this is our viscous forces. This you don't have to remember actually. Okay, you just try to understand how we are deriving a equation for fluid flow in a channel or in a pipe. That final equation you will have to remember, not this one. But how we are arriving at that equation, that is important. You should understand that one. Okay. So you see, this is our force due to gravity, this is force due to pressure, and this is viscous forces. Okay. Viscous forces will come from our shear stress only. So shear stress is tau equals to mu dou u by dou x or dou u by dou y. Okay, now double derivative, like here the equation, like we have represented pressure, no, dou p by dou x multiplied by volume. In similar way, when you see the derivation here, it will be dou tau by dou y and then multiplied by the volume. Okay, now tau can be replaced like this, so it will become mu dou 2 u by dou y square. So you see dou 2 u by dou y square, one of the term you can see mu dou 2 u by dou y square. So in three dimension, all three terms will come. So I'm just giving you one of the explanation for one of the term here. Okay. So this is how we are getting our Navier-Stokes equation in x direction. Okay. Now this represents Navier-Stokes equation in, and actually it is very easy to remember. Okay, it is very easy to remember. It's not like very tough to remember this particular equation. You see how this is written per unit volume. Okay, now you see this is density multiplied by acceleration per unit volume. So mass into acceleration, that will be written as density multiplied by acceleration. So this is density. Now this term is what? This is acceleration, no? And acceleration we have seen, no? This acceleration in x direction, how to calculate? Dou u by dou x, sorry, u dou u by dou x plus v dou u by dou y plus w dou u by dou z. Is it not? This is our convective term, and plus dou u by dou t, this is our temporal term. Do you remember our acceleration in x direction? In second chapter only we have seen fluid kinematics. So this is our acceleration only, na, x direction. So we can see same thing is written here. So this is density into acceleration. Okay. Now, right hand side, if you see force due to gravity, which is what? Mg. You will not write mg. You will write what? Density into g, because it is per unit volume. So you see density into g is written in x direction. Pressure forces. Pressure forces is gradient of pressure multiplied by volume actually. Okay. So gradient of pressure multiplied by volume. So it's not pressure multiplied by volume. It is gradient of pressure multiplied by volume. So dou p by dou x and per unit volume. So that volume term, volume thing is not there. That factor is not there. And then the viscous forces. Viscous forces is what? See, shear stress is mu dou u by dou y. And I have explained how it becomes mu dou to u by dou y. Like this I have explained. So from here you can remember it is double derivative of u. One of the term you can remember. So it is mu dou to u by dou y square. Shear stress, if you remember, then this also you can remember. So mu dou to u by dou y square. Similarly for dou to u by dou x square, and similarly dou to u by dou z square. Like this you can remember. Navier-Stokes equation in x direction. Is it easy now to remember? Okay. So similarly, we can write in y direction also. You see, I have not written ay, I have not expanded like this, but you can write now. It only thing here it will be replaced at v. That's all. Otherwise, right hand side also density into gy, dou p by dou y. Only thing you see pressure always with a negative sign it will come. Okay, because in flow direction pressure reduces. That's why that negative sign comes. Okay, so minus dou p by dou y, and then this is same thing is there. Okay, similarly in z direction. So all three direction equation you can write straight away. You can write. And in vector form, we can write all the three equation in one single equation, which is this one. This represents all three equation. Okay, this represents all three equation. Here is the this is a total derivative of v, so it is total acceleration, not ax, ay, z. It is net acceleration, which is root over ax square plus ay square plus 8z square. These three are equation in all three directions. Is it clear? Now, next is, if we consider flow in a channel, let's say this is our channel and we are considering flow in a channel, or we can consider, let's say, flow between parallel plate. This is our fixed parallel plate. This is fixed. This is also fixed. Okay. So flow between two parallel plate we are considering. Okay. Okay. This red line should be here, not here. Okay. Now you see the gap between parallel plate is 2b. This direction is y direction. This is flow direction is x direction. Now we'll try to find the exact solution of Navier-Stokes equation. So we are going to solve the differential equation. We are going to solve the differential equation. Now it is very difficult to solve the Navier-Stokes equation. That these three equations what we have seen is very difficult to solve. So what we'll do, we'll try to uh, assume few things, or we'll try to neglect few terms, so that our equation reduces to few terms only. Okay. And I have told you that for solving any fluid flow, two equation we need to solve simultaneously. That is conservation of mass or continuity equation and conservation of momentum, which is our this here it is Navier-Stokes equation. So you see, first is continuity equation, and we are trying to solve problem for parallel flow in a straight channel, parallel flow in a straight channel, or flow in a flow between two plates. Okay, now we are assuming, first thing we are assuming is steady flow, incompressible. Okay, steady flow, incompressible, and variation in z direction is neglected. So z direction is what? Into the slide, into this slide. Okay, y is this one, x is this one, so z is into the slide. Okay, in that direction the variation is neglected. Obviously here you can see this is my z direction, this is my x direction, and this is my y direction. Okay, so the fluid, see, as it is moving in this direction, there will be a variation of velocity, pressure, and all those things. In y direction also we can see some variation, but in z direction, as this dimension is very large, the variation in very less. So we are neglecting any variation in z direction. This is the first assumption we are making here. Okay, not first assumption. Like these assumptions, there is steady flow, incompressible, and variation in z direction is neglected. If we are considering variation in z direction as 0, then, and one more thing, all fluid particle move in one direction, that is x direction only. This is our assumption. Okay, these are assumption, because after solving this, we'll try to find the equation of Cotte flow, which is important one. We are trying to derive the equation for Cotte flow, and then we'll try to derive the equation for Hagen-Poiseuille flow. So that's why this thing is important. So you see, uh, if we are considering all fluid particle moves in x direction only, if all fluid particle moves in x direction only, not in y or not in z direction, then velocity in y direction, velocity in z direction is 0. This is also one assumption. The moment I put u and v as 0, now you see this is my continuity equation. If v is 0, w is 0, then dou u by dou x is 0. If dou u by dou x is 0, that it means that velocity is varying in y direction only, in this direction only. Okay, and that's why this profile is coming like this. In y direction it is coming like this. Okay, velocity is varying in this direction, velocity is not varying in x direction. You see, at this location also, if I make the profile, it will come like this only. Here also, if I make the profile, it will come like this. So at this x distance, the profile is this. At this x distance, profile is this. At this x distance also, profile remains same. But if I move in y direction at any location, like in this at this point, if I move in y direction, you see velocity here is 0. Here it is minimum. Again, here it is varying in y direction. So profile will come something like this. But what is the name of the profile? That we need to derive. So you see, dou to u by dou x square is 0. So double derivative of that also will be 0 here. And dou to u by dou z square, because in z direction we are not considering any variation. So this will be 0. As dou to u by dou x square, dou x is 0. So this term is 0, this term is 0. All these terms will become 0. And then we'll put all these assumptions in this 3 equation. Because to solve a fluid flow, we'll have to solve this equation, this 3 equation, which is conservation of momentum equation, and then conservation of mass equation. Okay, so finally we'll get 3 equations. So from here you will have to start remembering things. Okay, first thing is this x direction. Quickly I will just tell you. See, this is our x direction equation. This was 0. Okay, this was 0. Okay, gravity in x direction, we are not, because gravity only in y direction we are considering, so gravity in x direction it is 0. Now steady flow, so this is 0. Dou u by dou x is 0, that we know. Variation in z direction, it is 0, that we know. So we are left out with only two terms, this term and this term in x direction. In x direction, only this two term. So you see, in x direction we are having, sorry, this also is 0. Oh, this term is also there, na? This term is also there. Sorry, this term was also there, this term is also there, and this term is also there. Now the moment we put mu and w is equals to 0, so this term also will become 0. So we are left out with only these two terms, and this two terms, this is force due to pressure and this is force due to viscosity. Okay, force due to viscosity. So only this two term we are having. Okay, so you see, force due to pressure, force due to viscosity, only two terms are considered in this fluid flow. Other things we are neglecting. So this is in x direction. In y direction, if you see in y direction, v is 0, so this completely is 0. Here also v will be there, because we'll write like this, no, ay we'll write like this, so all v will be there here, so this term will also be 0. And gravity effect in this small channel will be very less, so that gravity effect, we are not considering gravity effect in this fluid flow, so this also will neglect. Okay, so this is also 0. So in this term we are left out only with what, minus dou p by dou y. Similarly, in z direction, all this w is 0, so this is 0, this is 0, this is 0. This also will become 0. Z direction gravity effect also we are neglecting. So again, we are left out with minus dou p by dou z is equals to 0. Very important thing I'm telling you, because these things when you see in your book, no, when you refer your book, they have derived in some different fashion. I will tell you that also, a quick derivation. Okay, but you should understand where from it is coming, that you should understand. Okay, it is important because they can ask questions from these things. Okay, so now if you see x direction, two terms are there, force due to pressure and viscosity. Y direction only pressure term, z direction only pressure term. Now this term represent what, dou p by dou y is 0, that means pressure is not varying in y direction. Okay, this also dou p by dou z is equals to 0, that means pressure is not varying in z direction. That means a very important conclusion, which is pressure varies only in x direction. So they can ask this thing. Okay, this they can. So if I would, I could have told you directly this particular thing, that remember this thing, that pressure varies in x direction only, but you should understand where from it we are getting. So from the basic derivation and neglecting all these things, by considering all these assumptions, we we arrive at this particular conclusion, which is pressure varies in x for what, flow in a channel or flow between two parallel plate. Is this point clear? This point you note, this particular point you can note, pressure varies in x direction only. For what? Flow in a channel or flow in a, so they can give in objective, flow in a channel or flow in a this thing between parallel plate, or in a Hagen-Poiseuille flow, or in Cotte flow, the pressure varies in x direction only, in all three direction, or pressure is constant, pressure is 0, like that they can give, because in gate exam they have asked in 1 mark question. So here also they can ask, because this objective means they can give this objective question. So is this point clear to you? Pressure varies in x direction only. Now you see, so we are left out with only this equation. This equation we need to solve. This tells you pressure is not varying in x in y and z direction. That's all. So this two term is not required to solve. Means you will integrate and you will get P is constant in Y, P is constant in Z. That's all. So this tells you the pressure is constant in Y direction. Pressure is constant in Z direction. That only it will tell. That's all. But this will tell you pressure is varying in X direction. Okay. So now from here, so you see, this is the equation what we are getting, and we'll have to solve this equation. But if you refer your reference books now, what they do is they will get this equation. They will get this equation, but what they will show you is that a fluid element like this and a forces acting and the element size like this is our fluid element, and pressure is this height is dx and pressure is acting here as px. Here it is acting as px plus dx. Okay. Here in this this direction a shear stress as tau y, and in this direction it is tau y plus dy like this. A shear stress is acting. So only these two forces are considered in that fluid element. But where from, like how you are neglecting other terms, why you are considering only these two terms, that you should know. So with that derivation only you will understand that why we are considering only pressure force and force due to viscosity and other things are neglected. Okay. So if we are considering only these two forces, then you see I will do force balance here. So pressure in this direction, I will do force balance in x direction. So you see in this direction due to pressure, see pressure is acting on this thing and unit width inside this width, no, this width is 1 unit. So that I will consider 1. So the area of this thing where the pressure is acting, this pressure is acting. So area of this one is what? Height is dy, like it looks like this only. You see, it looks like this, and from here a pressure is acting. So height is what? Dy, width is what? 1. So the area of this thing, this the face is what? Dy multiplied by 1. So dy multiplied by 1, and the pressure, the differential pressure between this face and this face is dp. So dp and similarly the differential shear stress between this and this is dy, and the area, like if you consider the area of this top surface, so top surface looks like this. Okay, top surface. So width in unit depth is what? 1. Depth will consider, depth is 1 unit, and this is what? Dx. So this area is what? Dx multiply 1. So dx multiply 1, and the differential this shear stress is d tau. Now you can rearrange this one and you will get this equation. Okay, and you can write tau as du by mu du by dy, and you will get this equation only, which is same as this equation. So actually we are getting this equation with the help of that Navier-Stokes equation. With that, all these assumptions, after all these assumptions, you will get this equation. But here, directly by considering this fluid element and this pressure, only pressure and shear stresses, and the force balance in x direction, you will get this equation. Now you rearrange. Now you rearrange this one. You can rearrange this equation like this. Okay. Or what I will do is, you see, this equation can be rearranged as d2u by dy square is equals to 1 by mu dp by dx, like this, because we want to calculate what? Velocity variation in y direction. You see, this is y direction, and we want to know what is the variation in this y direction. You see, there is a velocity variation in y direction, and velocity at this point, at the at the fluid contact in that the fluid is in contact with our wall or plate, there the velocity is 0. Here the velocity is 0, and at the center it will be maximum, and that only we need to derive actually. So sorry. So here if you see, we'll have to integrate this one to get the velocity profile. So if we integrate one time, this will become what? Du by dy. After first integration, we'll get du by dy. Okay, and this is equals to 1 by mu. And now you see here only whatever we have assumed that pressure varies in x direction, or the differential of pressure in x direction is constant. So the dp by dx, the pressure gradient in x direction, is constant. This is also one more important conclusion you should remember. They can ask in GATE, they have asked this question in 1 mark question. Okay, in 1 mark they have asked. So two things you can remember from here. One is pressure, pressure, pressure varies in x direction only. This is the first thing. And the gradient of pressure in x direction is constant. It is not zero, it is not variable, it is constant. Okay, this thing you should make a note of this point, particular point. Okay, they can ask the two very important conclusions regarding pressure. Okay, so the pressure gradient is constant. The moment we consider pressure gradient as constant in fluid flow, which fluid flow? Flow between two parallel plate, then we can treat this particular term as constant. Then if we treat this particular term constant, this particular term as constant, then we'll get what? 1 by mu du by dy, sorry, 1 by mu dp by dx, then multiply by y because everything is constant, and then plus 1 constant because this is a indefinite integral. So after integrating, just again I will tell you, after integrating this one, left hand side will become what? Du by dy. Right hand side, all these things are constant, so it will come out of integral, this thing, and we'll left with what? Y only. Plus 1. Now again, we can, as we want to calculate velocity, we'll have to integrate it one more time. If you integrate one more time, this will become what? U. This will become what? This is constant, so 1 by mu dp by dx. This will become y square by 2 plus c1 into y. Integration of this one will be c1 into y plus c2. Okay, now we need to find two values of these two constants, c1 and c2. So we should have two boundary condition. We should have two boundary condition. So the boundary conditions here is, you see these two plates are fixed. So velocity at this point and this point is what? 0. And we have considered our coordinate at the center. We have considered our coordinate at the center. So you see at y equals to minus b, you see this is 0. So this is minus b and this is plus b. Okay. So at y equals to minus b, velocity is 0, and y equals to plus b, velocity is 0. So y equals to minus b, velocity is 0. Y equals to plus b, velocity is 0. The moment we put this two things in our derivation, in this equation, we'll get the value of constant, and finally we'll get the equation which you have to remember. Okay, the final thing you will have to remember, in a fluid flow between parallel plates, which is this equation. Okay, so this is what? This is which equation? Which curve? It represents which curve? Variables are u and y. So which curve is this? Like I'm asking parabola, hyperbola, ellipse, circle, like that, straight line, like that I'm asking. It is parabola. Because y, like you can consider y equals to 4a, y square is equals to 4x type. Okay, so one of the variable highest power is 2, one of the variable highest power is 1. So u highest power is 1, y highest power is 2. So this is parabola. So they can ask velocity profile in fluid flow with parallel plate. It is which profile? It is parabola. Okay, it is parabola, and this is the equation, final equation. So again, I will revise you the points you should remember in this particular topic. Which topic? Fluid flow between two fixed parallel plate. Two fixed parallel plate, fluid is flowing. Okay, so points to be remembered again. First point to be remember is only two forces are considered, pressure force and force due to viscosity. Only two forces, pressure force and force due to viscosity already. Second point, pressure varies in x direction only. We have derived this thing already. Pressure varies in x direction only. Pressure in y direction, it is constant, means it is not varying, it is constant, means variation is zero. Dou p by dou y, it is zero, and dou p by dou z, it is zero. Pressure varies in x direction only, and pressure, the variation of pressure in x direction is constant. It is not zero, it is not variable, it is not something else, it is some constant value. So two things from here related to pressure. Pressure varies in x direction only, and pressure gradient is constant. Clear? The second point. Okay, make a note of this one. The third point is the velocity profile. The velocity profile here is parabolic. The third point, velocity profile in a fluid flow between two fixed parallel plate. It is parabolic. The third point you should remember, and this is the equation. Third point. Noted? And the it should be here. This red line should be here. It's not like that. It should be here. So at the ends, the velocity is 0 because of no slip boundary condition. At the center, it will be maximum. That maximum thing also will see. Now, if we want to calculate maximum velocity, so you see maximum is at the center only. So coordinate system is at the center. So here, so you put y equals to 0 here. The moment you put y equals to 0, you will get u equals to u max. That u max will be minus 1 by 2 mu dp by dx multiplied by b square. This is the equation for maximum velocity. You don't have to remember. You just remember this equation and put y equals to 0. You'll get maximum velocity. Okay. Now, similarly, we can derive the average velocity. Now, what is average velocity? Average velocity is, you see, we are having a velocity profile like this, a parabolic one. Okay, a parabolic one. So at the ends, it is 0. Here it is 0, here it is 0, but at the center we have maximum. So what will be the maximum at this end? What will be a what will be the average value? Some average value we need to calculate. Because like we at this location, at this x location, we don't want to take zero value, we don't want to take maximum value, we want some average value. So what is that average value? That average value can be calculated with the help of continuity equation, which is, see, volume flow rate is given by area multiplied by what? Average velocity. Whenever you are writing this continuity equation, the equation q equals to area multiplied by velocity, this velocity is what? Average velocity. It is not maximum velocity, it is not that minimum zero velocity, it cannot be zero, but it is always a average velocity. So again, you can use this equation. Okay, so average velocity will be what? Discharge by area. So that discharge by area, with the help of that, and again you can do small integrations. With the help of that, you can calculate the average velocity, which is this thing. Again, this also you know don't have to remember. Okay, what you will have to remember? You will have to remember this thing. When you compare this average velocity and maximum velocity, you take the ratio of these two, what you are getting? 2 by 3. So you see, average velocity, obviously it will be lesser than maximum velocity, because you may confuse in examination whether it was 2 by 3 or 3 by 2. So you should remember, average will be lesser than maximum. This is maximum, so always it will be higher than average only. So this ratio is average by maximum is 2 by 3. So they can ask fluid flow between two fixed parallel plate. What is the relation between average velocity and maximum velocity? It is 2/3. So this is the fourth point you should remember. Clear? The fourth point you should remember. Average by maximum is 2/3. Noted? So you don't have to actually remember this equation. You don't have to remember this equation. You only have to remember the general parabolic equation, which is this thing. You only have to remember this particular equation. Put y equals to 0, you will get maximum. And then you multiply by 2/3, you will get average velocity. Simple. Now, as the fluid is flowing, in this between these two parallel plates, so we get the velocity profile here. So velocity profile, it is parabolic. In the center we are getting a maximum value. Now we can calculate shear stress also. So shear stress, it is obviously it will be maximum where? It will always be maximum at the walls. Okay, it will always be maximum at the wall. So shear stress, if the center, the shear stress will be minimum, which is 0. So at the center, it will be minimum, and the wall, it will be maximum, because viscosity effects are seen maximum where? Near to wall only. No? Here only maximum shear viscous effects are seen, and it reduces towards the center, always reduces towards the center. And at the center only, we have minimum shear stress. At the wall, we have maximum shear stress. So the profile here, with the derivation, when you see, with the derivation, you can see that the shear stress is varying linearly actually. It varies linearly. So the shear stress variation will be linear, and it will be something like this. It is linear and it is maximum at the walls. What you have asked? Just one thing. Shear between two fluids are not there. That's why it is 0 here, you see, at the center. And at the walls only it is maximum. This represents the value, now this distance. It is reducing. At the center it is 0. Okay. So the fifth point is shear stress varies linearly, and its profile is this one. Its profile will be something like this, like K, which shows at the wall the shear stress is maximum, at both the walls shear stress is maximum, at the center shear stress is 0. This you can note. Okay. Noted this point? Shall I move to next topic? Okay. Now we'll start Corte flow. Now what is Corte flow? So in GATE, they have asked 2 times this particular question. What is Corte flow? Okay. In 1 mark question, they have asked twice. So here also they can ask. What is Corte flow? Corte flow is when one of the plate is fixed and another plate is moving with some velocity u. See, in last problem, both the plates were fixed. In this particular problem, one of the plate is fixed and another plate is moving with velocity u. This particular case is known as Corte flow. Okay, so the very first thing you can note is that when one plate is fixed and another is moving with some constant velocity u, then that particular flow is known as Corte flow. Now here also you don't have to go with the derivation and all those things. This itself is example like practical example. It will be different, difficult to tell you here, because means here like you have some channel here, not channel, some plate is here, and here also some plate is there, some fluid is there in between, and then top plate you are just pulling with some velocity at some moment. Then what happens? The fluid which is in contact with, like all the fluid which is in contact with this top wala layer will start moving with this one in this direction. But the fluid which is in contact here, this will be zero. So the boundary condition here will change. So the boundary condition here will be, here it will be zero because this plate is not moving. This particular plate is not moving. It is fixed. Okay. So here the velocity will be zero only. But this will not be zero. This will have some velocity here, which is the velocity of plate itself. So this is moving with some velocity u. Okay. So this only you should make a note here for Corte flow. Bottom will be zero. So the velocity profile will be parabolic only. But here it is zero. At this point it is zero. Top layer will move with some velocity which is equal to your velocity of that plate only. This is the first, the second point you can note. First is what is Corte flow. Second is the profile is parabolic, but boundary condition you can understand from here. The third point is the maximum velocity will not be at the center. It will be shift towards upper plate or the plate which is moving with velocity u. This is the third point you can note. This thing only you will have to remember. All this equation derivation is not required. They are not going to ask these things in HL exam. Whatever is required, I've already explained. Okay. So these 3 points you can note down related to Corte flow. Okay. Now in Corte flow, actually the profile can be like this. The velocity profile can be like this. It can be like this. It can be straight line, and it can be like this, what we have seen in last slide. Okay. So if it depends upon different conditions. So if positive or adverse pressure gradient is there, positive or adverse pressure gradient. You see, in every equation we are having this pressure gradient. dP by dx is pressure gradient. So they can ask in Corte flow, if pressure gradient is greater than 0 or positive, we call this as adverse pressure gradient. Adverse means what? Which is viprit, which is ulta. Okay, like fluid is trying to move in this direction. Fluid is trying to move, but if I compare this location and this location, here pressure is more and here pressure is less. So the delta P is positive. Like delta P is what? P final minus P initial. So final is this one, means at this point PF. PF, and this is PI. So here it is higher, here it is lower. So the value will be greater than 0 only. So this is positive pressure gradient. And this is adverse because fluid is trying to move in this direction, but in this direction pressure is more, and in this direction it is less. So pressure is not allowing the fluid to move. It is not helping the fluid to move. So this is adverse pressure gradient. And if there is so much adverse condition is there, then locally in downward direction where the plate is fixed, here locally the fluid will move in ulta direction, and at the top the fluid will move in plate direction only. And that's why we are getting a profile like this. Up to this much location we'll get reverse flow. In this location we are getting flow in plate direction only. So they can ask when we'll get reverse flow. We can get reverse flow in condition when pressure positive or adverse pressure gradient. This point you can make a note. Now next is, if pressure gradient itself is zero, what happens if pressure gradient itself is zero? If this itself becomes zero, then you see this term will become zero. If this term itself, you see dp by dx is zero, so this term will become zero. Then we left out with u by this is equals to y by h. So the profile will become linear. So the velocity profile will be linear. When we'll get velocity profile as linear? When pressure gradient is zero. So this also you can make a note. This point also you can note. When pressure gradient is zero. When it is positive, reverse flow. When it is zero, then the profile will be linear. And third point, when the pressure gradient is negative or favorable pressure gradient. Negative means what? Here the pressure is more, here the pressure is less. So final minus initial will be negative only. This point minus this point, it will be, it is not final minus initial. Just like I am telling, this location minus this location, it will be what? Means lower minus higher, so negative. So it is favoring the flow. In this direction only net pressure is there, and fluid is also moving in that direction. So we call that as favorable pressure gradient or negative pressure gradient. In this case, we'll get parabolic profile, this profile. Parabolic velocity profile. So you can note this point also. So in adverse case, reverse flow. In zero pressure gradient, linear velocity profile. In negative or favorable pressure gradient, parabolic profile. Any one of you have studied this particular topic first time, or these particular things? Okay. Okay. These things are there in GATE syllabus also, it is there. Okay. So this is over now. Cotte flow is over now. Now next is we want to study about Hagen-Poiseuille flow. Okay, Hagen-Poiseuille flow. In Hagen-Poiseuille flow is flow in a pipe. When fluid is flowing in a pipe, no, that is your Hagen-Poiseuille. Okay. I don't know what they call Poiseuille or what. I'll call it Hagen-Poiseuille. Okay, so here, as the fluid is moving in this pipe, so we'll have to consider cylindrical coordinate rather than Cartesian coordinate. So whatever we were studying, or whatever equation we have seen for Navier-Stokes equation, that was in Cartesian coordinate. Cartesian means XYZ coordinate. First, we'll have to see cylindrical coordinate system. So we'll not go in detail. I'm just telling you, like for acceleration, we have studied no acceleration equation. So this 3 represents acceleration in your cylindrical coordinate. This equation represents continuity equation in cylindrical coordinate, and this 3 equation represents Navier-Stokes equation in cylindrical coordinate. Okay, and then this equation only will, this 3 only will again have to make assumptions. What assumptions we have made for flow between two fixed plate, and then we'll reach the equation which is similar to our that flow between two fixed plate. Okay, so this you can take a screenshot, or you will get these equations in any standard book. Okay, if you need any explanation, because this is not important means if not important for your HL exam, so I'm skipping this particular thing. But if you need explanation, you can ask me in WhatsApp. You can ask me. Okay. Now next is uh, Hagen-Poiseuille flow. So here I have already stated that here we'll have to consider cylindrical coordinate. So again, chota wala derivation we can do. We can consider a fluid element, what you can see in general books, a fluid element. But here fluid element looks like this cylinder, small cylinder. Okay. Again, he will consider the pressure. Pressure here will be Z, will be Pz plus dz. Okay, and at the surface we'll have shear stress. Now at the surface we'll have shear stress. Here it will not be like here T R, and here it will be T so tau R plus dr, like that. It will not be. Shear stress will not vary like this here and here, because this is same surface, outer surface. It will vary in radial direction actually. At the center again it will be 0, at the surface it will have maximum. But don't get confused, like in our cylindrical, in our channel, we have seen that when we have considered the fluid element, here it was having shear stress as tau y, here it was having tau y plus dy, some other shear stress. But in this fluid element, it is a same surface no throughout the cylinder. So here it will not be different here and here. It will be different at the center and maximum at the surface. Now again we can do the force balance in Z direction. Force balance in Z direction. Same thing. Pressure multiplied by this area. Now this area is what? A circle. So pi r square. So radius of this small element, fluid element, is r. Radius of this fluid element is r. So pi r square is area multiplied by dp, the pressure gradient in this direction. D pressure, and shear stress at the surface. It will be what? Shear stress multiplied by the circumference surface area. Circumferential surface area. Okay, that is what? 2 pi r, and then the length of this one, which is dr. Length we have considered as dz. Length we have considered as dz. So length is dz. Length of this one is dz. Okay, and length multiplied by circumference 2 pi r. So 2 pi r multiplied by dz will give us the force due to shear stress. So this is the equation. This is the equation. Now again this tau you can write as mu du by dr. Mu du by dr. You can write like that, and you can rearrange, and you will get again the equation like this. Okay, which is similar to, you see, final equation. You will have to integrate this one. At the center, velocity will be maximum. At the radius is 0. with this boundary condition, you can integrate, and you can, with this boundary condition, you will get the final equation. So final equation only you'll have to remember, which is this thing, which you can see is that, which is same as your this case, which is same as this case. Okay, only difference is here it is 2, there it is 4. Otherwise, that equation is, for Hagen-Poiseuille, the equation is u equals to minus 1 by 4 mu dp by dx r square, capital R square, minus a variable radius square. Same equation, only thing here it is 4. So you have to remember only one equation, velocity profile. Then you can remember velocity profile for Hagen-Poiseuille also. So the first thing you should remember here is the equation itself. Clear how to remember the equation? Which the second point, which profile it is? Parabolic. Again, the velocity profile is parabolic. At the wall, the velocity is 0. At the center, it is maximum. Okay. So again, if you want to calculate velocity maximum, put radius 0, because here we have cylindrical coordinates. So this is the radius 0. So put r equals to 0 in this equation. The equation what you will get is the maximum velocity. This is the maximum velocity. Okay. Again, you want to calculate maximum velocity, sorry, average velocity. Same, with the help of your discharge, which is equals to area multiplied by the average velocity. So with the help of this, you can calculate your average velocity with little mathematic term, means mathematical calculation will come. You can do this one. Okay, with this element only, you will have to integrate from 0 to complete r, and you will get. Now, after integration, you will get this. Okay, so average velocity here, it is average, the ratio of average by maximum is what? 1 by 2. There it was 2 by 3. There it was 2 by 3. Here it is 1 by 2, half. The average velocity is half of maximum velocity. In case of what? In case of Hagen-Poiseuille flow. One more point you can remember. You see, at the center, at r equals to 0, we are getting maximum velocity. At which radius? Which radius the velocity will be average? At which radius you will get the average velocity? Like here, let's say, what I'm trying to say is, at the wall it is 0. At this point, let's say it is 2. So average will be about 1. So you see it is varying from 0 to 2. It is varying. Average velocity is what? It is 1. So 1 will be somewhere here. So at what radius? At what radius? From here, at what radius? This is you are getting this average velocity, one velocity. That one velocity we will get at r by root 2. So this point also you can remember. Average velocity you will get at r by root 2. Maximum velocity you will get at r equals to 0. Third point, ratio of average by maximum is 1 by 2. And profile is parabolic, that we have already seen. Clear? You can note and then let me know when I can proceed further. See the points what I am telling you, from there only questions comes. This questions, this comes from these points only. Even in GATE also they are asking from these questions only, right? These topics only. And when fluid is flowing in this pipe, If Reynolds number is less than 2300, flow is laminar. If it is greater than 4000, flow is turbulent. In between, it is transient. Okay. Now, next is, again, we'll have to see the shear stress also. So shear stress is directly proportional to R, which tells you shear stress varies linearly. Shear stress varies. So this is my pipeline. And if at any location, if you want to plot your shear stress, at the center it will be maximum. So this is tau max. Okay. So, and it is varying how? It is varying linearly. So this point also you can note that in Hagen-Poiseuille flow, shear stress varies linearly. At the center it is 0. At the wall it is maximum. Okay. Now one more important derivation here. You see, this is our average velocity, which we will get from last slide only. This is the maximum. Maximum is this one. Average will be half of this. So divide by 8 will come. Okay. So U average will be what? This R square by 8 mu and minus dP by dz. Remember, this is not dou P by dou Z, it is dP by dz, because pressure varies only in flow direction. Is not varying in other radial direction. It only varies in flow direction. Okay. That point also you can note. Okay. Now next is, this is our average velocity. Now we can rearrange and put dP by dz, the pressure gradient, in left side and other terms in right side, right hand side. Now we are focusing on fluid flow in a pipeline. Okay. So for this length, let's say this is my dz or length L. Let's say this is length L. So for this length, there is a pressure drop which is dP. So total drop is dP by dz for dz length. Total length, if I consider, it will be delta P by that L length. Okay. Now this represents pressure drop in this length, pressure gradient in this length, which is this equation. So if they ask you what is the pressure gradient for this length, you can just rearrange this U average wala equation and you can get the equation for pressure gradient. This is the first thing. So for finite length L, see, this is for small length dz. For finite length L, the pressure gradient will be what? P2 minus P1. Here it is P2. So it will be what? P2 minus P1 by L. From here I am writing P2 minus P1 by L is equals to, right hand side, 8 mu U average by R square. Simple. Okay. Now what I am going to do is I am simply dividing right hand side. I will first take this L here. I am dividing right hand side and left hand side by rho g. This I can do. Okay. Now what is this? You see, P is what? Rho g H. So P by rho g is what? H. Pressure head. So P2 minus P1 by rho g is what? Pressure head loss. So P2 minus P1 by rho g is what? Head loss, which is 8 mu U average L by rho g R square. Now the Darcy friction factor, the Darcy friction head loss. Very important equation. Very important equation. Darcy friction head loss. The major loss, what we have seen in last class. It is HF FLV square by 2 dg. Now if we compare this equation and this equation, if we compare this equation and this equation, left hand side is HF, here also left hand side is HF. So right hand side we can compare. When you will compare, no, this friction, Darcy friction factor. See, Darcy friction equation is F L v square, which is average velocity, v square by 2 dg. FLV square by 2 dg. You remember this one, FLV square by 2 dg, FLV square by 2 dg, like that you tell 5-6 times. You will remember this equation. Very important equation. Head loss in a fluid flow. Okay. So FLV square by 2 dg. In this F is Darcy friction factor. Okay. Darcy friction factor. That Darcy friction factor we can calculate in terms of Reynolds number. So if I compare this one and this one, I will get this as equation, which is left hand side is Darcy friction factor F and right hand side is 64 by RE. So here they can ask you, if Reynolds number is 1000, if Reynolds number is 1000, then what is the value of Darcy friction factor? They can ask. And in GATE, they have asked. Clear? What is the equation for Darcy friction factor? It is 64 by RE in terms of Reynolds number. If you compare this one and this one, if you compare and you just do the rearrangement, you will get this one. Where RE is what? Reynolds number, rho VD by mu. This you might have, you may remember, no? Reynolds number equation. Rho VD by mu. This V is average velocity only here. So you can make a note of this one. Yes, if RE is given as 1000, let's say RE is given 1000, then F will be what? 64 by 1000. So the value will be 0.064 F value. They can give in option. How much time it will take to calculate? Hardly 2 seconds. Okay, so this is for first thing. Now, as I think Naveen only asked in last lecture, that sometimes you will see this equation also, HF equals to 4F V average square by 2 dg. You may have seen this also. Here I am writing FLV square by 2 dg. But sometimes in some book you will find 4 FLV square by 2 dg. Have you seen like this? Here this F, it is not Darcy friction factor. If it is FLV square by 2 dg, then this F is Darcy friction factor. But if it is 4 FLV square by 2 dg, then this F is not Darcy friction factor. It is fanning friction factor or skin friction coefficient. So better to write this as, instead of F, you can write 4 CF. Skin friction coefficient, which is CF. 4 CF L V average square by 2 dg. So this F is, if 4 is there, this F factor 4 is there, then this friction factor is not Darcy friction factor. It is Fanning's friction factor or skin friction coefficient. So if I compare this with our this equation, what I will get? Darcy friction factor is 4 times skin friction coefficient. So you can make a note of this also, the relation between these two. In gate class, I go in much more detail. Means everything I explain in detail. Here I'm just trying to save some time. That's all. I'm just trying to save some time. That's all. So that in remaining time we can solve, like we can utilize in solving questions. That is more important right now. Okay, so this is over, I hope. So I hope all points related to Hagen-Poiseuille you have noted. Uh, Next comes the questions. Okay, so just 5 minutes, five more minutes. Okay. Are you there for 5 more minutes? Okay, these questions are there which we have uh, which are related to the topics which we have studied in last lecture. Okay, this we have already studied. Okay, you can tell the answer for 392. Yes, it should be this one, but I think there is some misprint. It is FLV square by 2dg. Answer will be this only, but just make a note here. It will be 2dg. Okay. Uh, you can tell me 397. Okay, head loss. First, this thing. Head loss in a fluid flow is experienced due to what all the reasons are there for head loss? It is, yes, it is due to friction also, change in direction also, head loss will be there. Okay, losses we have seen, no? So this is major loss. This comes in minor losses. These things, change in section of passage or obstruction. These things. Okay, so all of them. Okay, 397. So head loss actually it should be proportional to. It's not equal to. It is proportional because head loss due to friction. No. So head loss due to friction is F L V square by 2 dg. Now L is constant, velocity is constant because uniform, no? Uniform diameter. So if diameter is constant, velocity is that is anyway it is average velocity, so that is constant only. So this thing is constant. Now F. So HF it is, so F thing is what 64 RE. So head loss is proportional to what 64 by RE. Okay, 16 by RE was 16 by 16 means that 16 thing you have seen for uh, even not 16 thing you have seen for CF was 16 by RE, F was 64 by RE. So HF, even if you use this equation 4 CF L V square by 2 dg. Now you use CF as 16 by RE. Now 16 if you put here 4 into 4 it will 16 into 4 will become 64. So it should be 64 by RE. Okay. We have seen na F is 64 by RE. Four 73. Volumetric flow is what? Discharge. Q. Q is what? Area multiplied by average velocity. Now you tell. See here what you will have to do. Area is pi r square. Yes, it is A. Pi r square and U average. So U average is what? General velocity. U is what? Your or maximum velocity. If you see, it is 1 by 8 mu r square dp by dz. Okay, 8 mu. The maximum velocity, no, 8 not 8 mu, it is 4 mu average velocity. Maximum velocity, sorry, maximum velocity is 1 by 4 mu. Average velocity will be half of this one, so 1 by 8 mu. Okay, r square dp by dz. This you put it here, you will get this equation. We have seen na average velocity r square by 8 mu. This is our maximum. Half of this is 1 by 8. So r square by 8 mu minus dp by dz. In this you multiply area, pi r square multiplied by u average. So you will get what? A option. Okay. Only one topic is left actually. In next class, we'll try to solve more questions first related to this topic only. In this fluid flow in a pipe, few questions will solve, and then we'll start boundary layer. Okay, that one topic only is left out, boundary layer, and small means very little description I will give for turbulent flow, because that is not important much. Means only few questions can come straight away. Questions can come for turbulent flow. Those things I will cover in next class. Okay, but in next class I will try to cover more questions related to this topic, then boundary layer and questions for that topic. With that, we'll complete our fluid mechanics. Okay. Okay, then. Thank you. Class was till 8 only, no? Yes, next class will be last class for FM.